As computer science folks, all of you are aware that theory in computer science means talking about hardness of problems, right. So, how hard is it to solve, and looking at space complexity, time complexity, right, and approximability, right. So, how approximate is the solution, those kinds of things, right. So, we are going to try and see if we can give such a flavor of theory to machine learning as well, right. So, we are going to talk about how hard is a problem to approximate, right. So, I have a perfect solution, right, but then I can get close enough to it, right, but how often can I get close enough to the right solution, right. So, that is one kind of question that people want to ask, and then there is another question on how hard problems are to solve in general, right. So, we are going to talk about hardness of problems itself, right. So, different measures of hardness of problems, right. So, typically we are interested in generalization error, right. So, what is generalization error? So, after the notes, right, this will be completely different notation from what I have done earlier in the class, right, but I will just stick with the notes and I will give you these notations. So, that is the generalization error of a hypothesis H. So, I will denote by epsilon the error function, right, and of H means the error of hypothesis H, right. So, the expected number of times the hypothesis will make a mistake, or the error of H, right, is the probability of the hypothesis H making a mistake on a data point x, right, when the data points x and y, right, where x is the input and y is the label, right. So, the data x and y is sampled from some underlying distribution D, right. We are assuming that this distribution D is fixed a priori and unknown, we know about all of this, right. So, we always talked about this, I talked about it as p of x comma y earlier, but here they are talking about the distribution as D. So, when the data is sampled according to this distribution D, so what is the probability that I will make a mistake, right. So, this is also the expected number of mistakes, because every mistake will count once, right. So, the probability of making mistakes will also be the expected number of right. So, this is essentially our error, the probability of, and this is what we call the generalization error, right. But typically what is the error that we have access to? We have access to something which is often called a we have access to only something called an empirical error, right, or sometimes denoted as empirical risk, right. So, which we will denote by epsilon cap, okay. So, epsilon cap of H is equal to right. So, where xi and yi are the ith data point given to you in the training set, right. So, the empirical risk for hypothesis H is the number of times. So, what is the 1 is the indicator function. So, 1 will be this function will be 1 if this condition is true, it will be 0 otherwise, right. So, essentially when will it be 1? Whenever I make an error, whenever H makes an error this will be 1, whenever H is correct this will be 0, right. So, I will add it up for all the training data. So, here I am assuming that I have m samples in my training set, right, and I will divide by m. So, this gives me the probability of me making a mistake as estimated from the training data, right. So, this is sometimes known as empirical error or empirical risk, right. So, typically I only have this quantity, right. So, whatever is given to me as a training data, right. So, I can have many ways in which I can estimate this error, but this is all I have access to. So, this is called the empirical risk. What I am really interested in is in the generalization error, right. So, what we want to know is how good is this empirical risk estimate that I make in terms of measuring the generalization error, or how close is it to the generalization error, right. This is a question that we want to ask. See, this has shades of hypothesis testing, right. There are shades of hypothesis testing, but so we are going to do a very different kind of analysis here, right. It has got shades of hypothesis testing, but the kind of analysis we do here will be very different, right. So, what we are, the question that we are asking is, okay. So, given that I can estimate empirical risk, right, what can I say about the generalization error, okay. So, before we go on to look at this in more detail, right, I want to introduce a couple of results which will make it easier for us to talk about. Oh yeah, before that let me talk about one thing. So, most learning algorithms that we have, right, most learning algorithms that we have do what is known as empirical risk minimization, right. So, the answer that you will typically end up giving is so you will have some hypothesis class capital H, right. Suppose you are looking at linear classifiers and your input dimension is say some p, right. So, then you will be essentially looking at classifiers that are defined by theta 0, theta 1, theta 2, or beta 0, beta 1, beta 2 up to beta p, and then given by inner product of that with the data point, and if it is greater than 0 you will classify it as one class, if it is lesser than 0 you will classify it another class. That is basically what linear classification does, right. So, when we looked at a variety of different linear classifiers, but at the end of it you will have something like that, right. You will have some beta transpose x, right, and then you will have some function of beta transpose x, and then whether that is greater than 0 you will put it in one class, if that is lesser than 0 you will put it in another class. So, that is essentially what the hypothesis class H would be, right. So, for example, in the case of linear classifiers, say in the case of neural networks, it will be all the classifiers that you can implement given the choice of number of layers and number of neurons per layer that you have made, right. You would have made some number of neurons, some number of layers choice, right. So, for different weights that you can set for all those different values you can set for all those weights, you will get a different classifier, right. That constitutes your hypothesis family script H, okay. So, what I typically would like to report is that H, okay, that has the minimum empirical error over all members of that family H, capital H, okay, and that H hat is the classifier that will report by doing empirical risk minimization, okay. So, this is essentially called empirical risk minimization. I mean, this is the ideal case, right. Obviously, we know that we do not get this, right. If you are using neural networks, you are training using back propagation on neural nets and stuff like that, you actually do not find the argument, right. You essentially have some approximation of it, then you just stay with it, right. So, likewise, depending on what classifier you are using, you might not actually find the minimum, right. What you are trying to do is minimize the empirical risk anyway, right, because that is the only thing that you can what that is the only thing you can measure, right. So, is it clear so far? The setting is clear, right. So, we would really like to get a classifier that is good according to this, right, but we are not able to do that. So, we look at empirical risk, right, and then we find empirical risk minimization and we get this, right. So, before I move on, I want to introduce a couple of results, right. So, the first one is called union bound is a very simple, all of you should be familiar with union bound, right? Yes, no, maybe? How many of you said yes? Oh, 2. Did you do union bound in probability tutorial? Huh? We did it in the probability tutorial, right? Anyway. Right. Let A1 to AK be k different events, then probability of okay. In most versions of probability theory, this is taken to be axiomatic. Okay. So, this is called union bound, right. So, it is equal when they are independent, right, or they are disjoint. Thinking of them as sets, they are disjoint. Okay. So, the next thing is right. So, the something which is variably called a Chernoff Hoeffding bound or the Hoeffding inequality or the Chernoff inequality. I mean some subset of these two and some subset of that will be used for describing this result, right. Did you do the Chernoff bound also in the probability tutorial? Maybe after I write the bond you will know. Huh? So, here I am stating this very specific to Bernoulli distribution, but the Chernoff bound holds for in general. Okay. There are other milder conditions, it need not necessarily be Bernoulli, but as far as we are concerned, we are only interested in binary outcomes, right. So, can you guess what is the outcome I am interested in? Correctly classified or not correctly classified. So, that is the outcome I am interested in. So, we are only considering Bernoulli case in this case, right, but this result is much more general, right. In fact, there is a version of it where you can also relax the independence assumption, but it gets more and more complicated. Okay. In fact, when you relax the independence assumption, you get some kind of, you get the chromatic number of the interrelationship graph enter the picture. Okay. I still have not figured out how the chromatic number enters the picture in that result. Okay. It gets really complicated, right. So, let us hope and pray that all the random variables you deal with are independent, or you can think of them like that, right. But in some cases that is not true, and let us worry about it. So, in this case essentially what I mean is, so the probability that some zi equal to 1 is say some phi, and the probability that zi equal to 0 is 1 minus phi, right. So, I will just keep it as some Bernoulli distribution parameterized by some phi. Okay. Right. So, what do we know about the Bernoulli distribution? Phi is also the mean, right. We know that phi is also the mean, right. So, typically the Chernoff Hoeffding bond is stated on the mean, okay, but this version of the Chernoff Hoeffding bond is stated on the parameter phi. yeah, but it's not in its role as the probability, but the phi is here used in the role of a mean. Okay, that is one thing I want you to remember, like I do not want you to look at the Chernoff bounds and then go actually flip through some other place and find that nowhere is the probability of outcome is mentioned, right. That will never be the case because the Chernoff Hoeffding bound is stated on the mean. So, what is phi hat? It is the mean estimated from these random variables, right. I mean this should all be familiar to you from the hypothesis testing case, right. So, this phi is the true mean of the distribution and phi hat is the mean that is estimated from these random variables, these samples that I have drawn, okay, correct. And that gamma be greater than 0, let some fixed constant gamma greater than 0, then so the probability that phi hat is away from phi by greater than gamma. Okay. So, what does this mean? Phi hat is away from phi by greater than gamma. It is 2 times e power minus 2 gamma squared m. Right. The 2 comes because this is a two sided inequality if you think about it, right. It is less than gamma or greater than gamma, right, both work, it is a two sided inequality, therefore the 2 comes. So, if you want to look only at one side then you can drop the 2 and then use only e power minus 2 gamma squared m, right. So, essentially what does it say? If I have lot of samples, right, if m is very large, right, I have e power minus m, so it becomes smaller and smaller, right. As m becomes large, the probability that my phi hat will be far away from phi becomes smaller and smaller, right. So, this gives you a way of quantifying how many samples I need, right, before the estimate that I am making, right, before the mean that I have estimated is close enough to, sorry, the mean that I have estimated is close enough to the true mean, right, with a high probability, right. So, gamma is something that I fix a priori, okay. Gamma is something I say, okay, I need you to be at least this accurate for me, okay. Now go and tell me how many samples I need. Alternatively, I can ask questions like, okay, I have so many samples, okay, then how accurate am I likely to be, right. Is it fine? Is it enough to fix the number of samples? It will be little bit more work, but so there are multiple things here. One is, okay, what is the probability that the error I am making is greater than gamma? So that is this quantity, right. So I need to supply gamma, right, and an error for me to find m. I need to supply m and an error for me to find gamma, right. Does it make sense? There are two quantities here, right. There are actually three quantities here. So, there is gamma, okay, there is m, and there is also the probability of the error, right. So, gamma is the magnitude of the error, right. Do people get that? Gamma is the magnitude of the error, and what is the probability that I am greater than gamma. So that is the third quantity, right. So I have number of samples, I have the magnitude of the error, and then I have the probability of making an error of that magnitude, okay, that is the left hand side, right. So I have 3 things here, okay. So this equation has 3 things here. So if I want to solve for gamma, so I need to specify the left hand side, okay, and I need to specify m, then I can solve for gamma, right. I say okay, I do not want to make a mistake more than 10% of the times, okay, that means my probability should be 0.1, okay, and I am only giving you 100 samples, okay. Then I will come back and tell you, okay, if you want to be correct 90% of the times, then you will have to say that even if I am so far away from the right answer, I am correct, okay, only then I can give you the 90% guarantee. So that is essentially what I mean by saying there are 3 things here, you have to specify any 2, then you can think about it in terms of the third one, okay, great. So now we have these 2 results for us, okay. So usually that probability is denoted by some delta, okay. So we have these 3 things. So we will start off a case where I have k, only k specific hypothesis in my hypothesis class, right. I am searching through a space of k. K can be very large, right. I am not telling you how small or large k is, but I have only k hypotheses in my class, and I am going to search through this. It makes it slightly easier for us to develop some intuition, right, and then we can go back and go on and talk about an infinite h, okay. So we want to look at how epsilon hat h corresponds to epsilon h, okay. For some hypothesis h, how does epsilon hat h corresponds to epsilon h, right, and I am going to fix some h belonging to hi belonging to h for the time being, right, and the Bernoulli random variables that I wanted here, as we mentioned earlier, are going to be defined by so the random variable z is if hi of x is not equal to y, then it will be 1, it will be 0 otherwise. So whenever hi makes an error, then this random variable will be 1, whenever hi does not make an error, the random variable will be 0, okay. So we can go ahead and or following their notation, and so we can go ahead and write zj for each xj as xi xj not equal to yj, right. So if you remember, we always make the assumption that the training data was given to us in an IID fashion, independent identically distributed fashion, right. From the very beginning we have been saying that training data is IID, each sample was taken independently of one another, and we use this fact even in the hypothesis testing case. Again we will use the fact here, and that allows us to apply the Hoeffding bounds, right, that allows us to apply the Hoeffding inequality. So what is it that we have? So I have, if I have m training points, like we said, we assume there are m training points, therefore I have these m independent identically distributed random variables, okay. What is the distribution that I am drawing this from? From the true distribution of the data, right. So I am assuming that all the points are coming from the true distribution of the data, right. All the training points have come from the true distribution of the data, right. So, that is something which is very important. These are the two main assumptions that we are making here. What is the first assumption? IID. The second assumption, the training data comes from the true distribution, right. So, and that is the distribution according to which I want to evaluate the generalization error, right. So, these are the two assumptions we make, right. Of course, we can always relax these assumptions. In fact, quite often we need to relax these assumptions because in real life you will not be able to satisfy either of the assumptions, right, but this is good enough to give us some kind of an intuition as to how things will work, right, and then we can worry about relaxing these assumptions later. Right. So, that is my epsilon hat hi. So, we know that, right. So, epsilon is already defined there, right. So, all I have done is taken whatever expression that was there in the sum there and defined that as Zj, and I get this. So, already we know that. So, what is epsilon h? That is the true mean, right, and what is epsilon hat? That is the estimated mean by taking m samples. So, I can directly apply my Chernoff the Hoeffding bounds, right. So, the probability that, what is my phi here? What is phi here? Epsilon h. Okay, we are considering a specific thing. Okay.
We ideally won't minimize the training error, but usually will won't try to overfit it, right? But this assumption of doing the argument of the empirical error will saying that we are trying to minimize the training error to 0.
Yeah. So, if you have a very large class, right, then you have to be very careful about minimizing the empirical risk, because you run the risk of overfitting it, right. So,
usually we make the validation set to be.
Yeah. So, so essentially what you are trying to do in many of those cases is try to get a better estimate of the error on the better estimate of the generalization error actually. So, when you are trying to do the validation, right, so you are essentially trying to get a better estimate of the generalization error directly. So, all of these things are essentially to give you some notion of what to say, some notion of the complexity of the problem that you are trying to solve. Okay, it just gives you some notion of the complexity of the problem that you are trying to solve, and you will see that in a minute you will see that, right. So, in fact, one way to avoid overfitting in neural networks is to have a very large training set, right. If you have lots of weights, then you need to have a very large training set. That will kind of fall out of this. Just give me a sec, let us finish this. So, what we are now shown here is that for a single hi from the hypothesis class, if I have a large m, right, then the error will be, the probability of having a large error will be small, right. So, or even say I will be pretty close, right, even for small gamma, right. Suppose I want to know what is the probability that this greater than epsilon hat is, the difference between epsilon and epsilon hat is greater than, let us say, 0.01, right. So, that is what I want to know. So, my epsilon hat should be within 0.01 of epsilon, okay. Then what I will plug in here is 0.01, right. So, e power minus 0.01 square, that is essentially getting to 0 or 1, right, essentially getting to 1. So, essentially what I am saying is the probability of the error greater than 0.001 is greater than 1. I mean, sorry, it is lesser than 1. That does not really tell me anything, right, it is just lesser than 1, right? Yeah, duh, I mean, I know that, right. But then if my m is very large, right. Suppose I want this to be 0.01, this is 0.01 squared, then I will, let us say my m is a million, right. So then what will happen is I will have e power minus 20 or something, right. So that is a small number, right. So that, so if I say I have a lot of samples, then the probability of my epsilon hat being 0.01 close to epsilon, right, will be high, right, or at, right, and what this states is the probability that it will be 0.01 away from epsilon is low, right. So the converse is, if it, the probability that it will be 0.01 close to epsilon will be high, right. So that is essentially the result that we are, what we have shown here using the Hoeffding bound. So I did not show you the proof of the Hoeffding bound, it is non trivial, right. So if you are interested you can look it up, right. It is not very hard, okay, I mean it is just have to work it out, right, that is all. So but once you accept that on faith, right, you have this result, but unfortunately this holds only for one particular HI, right, that is not very interesting. I am essentially, what I have shown is you can give me like a 10,000 different hypotheses, and I can show you for one of those hypotheses, if I have a lot of samples, then I will be close. What I really want to show is, okay, if you give me 10,000 samples or give me 1,000,000 samples, for every hypothesis in this hypothesis class I will be close, right. For every hypothesis in the hypothesis class I will be close. So how are you going to do that? Use the union bound, right. So what I will say is I will define my the event AIs, right, I need those A1 to AK, right. I will define the event AI as so I will define this event AA as epsilon and epsilon hat being more than gamma away, right. So now this becomes probability of AI, right. Now this is essentially becomes probability of AI is less than or equal to 2 e power minus 2 gamma squared m, right. So now I do union bound. So what is the union of A1 to AK, right? What does it mean? At least one of them giving a higher error, right? So essentially this reduces to, there exists H, right, such that so say some HIs, okay, okay, now at least one H, right, so probability of at least one H, so that is what this there exists stands for, right. There exists means there is at least one H for which the error is large, right. So this is essentially equal to the probability of okay. So the probability that there will be at least one error, I mean at least one HI which has a large error is bounded by 2k e power minus 2 gamma squared m. For one of them it is 2 e power minus gamma squared m, right, 2 gamma squared m. Now for k of these it is just k multiplied by k. So this is essentially what we get from union bound. Okay. So now what I need the probability that there does not exist in any classifier that makes a large error. If I give it m samples, okay, there does not exist any classifier that gives a large error. So what will that be? 1 minus this, right, similarly 1 minus that, right. So the probability that does not exist hi okay. Yeah, is it clear what we have done here? Right, just a simple algebra here, right. So we got this, and so this kind of a result which holds for all h in the complexity class, I mean in the hypothesis class we have taken, right, because this result holds for all h in capital H, right. These are called uniform convergence results, right. So this is a uniform result because it holds for everything in the, this is more like a single result, right. This is for a specific hypothesis, while this result that we are giving you, that 1 minus 2k e power minus 2 gamma squared m, that bound is for all hypotheses in this hypothesis class. So this is called a uniform convergence result. Okay, when somebody says uniformly convergent, that means that it works for all classifiers, right, works for all classifiers. Okay. So far note that I have not actually talked about finding the classifier, right. So what is epsilon? Epsilon given a classifier, what is the error the classifier will be making in the overall population, right, and epsilon hat is the error that it makes on the training data. So I am just comparing the two, right. I have not actually talked about finding the classifier, right. So what we should be looking at is, we should be looking at comparing okay, I'll come to that in a minute. Right, if you remember I said there are like 3 quantities in the beginning, right. So now I am interested in solving for m. I want to know how many samples I can draw before I can give a certain guarantee on, I can give a certain guarantee on the performance, right. What I mean by performance here? What I mean by performance here? Whether my empirical error is close to the generalization error. I am not talking about the best generalization error. When I am talking about performance here, I am talking about whether my estimated error is close to the true error. Okay. So how many samples should I draw before I can give some guarantees on the performance of the estimator. Okay. So I want to solve for m, right, and what do I need to fix? I need to fix gamma as well as the error probability as well as this guy, right. So k is fixed for me, right. I given you the hypothesis class, right. As soon as I give you the hypothesis class, k is fixed for me, right. So I am going to say is that the probability should be at most, this quantity should be at most delta, some delta, I will give you the delta. So this quantity I will fix, So, the probability should be 1 minus delta, right, and I will give you the gamma also, right, solve for m, right. So, delta will be right. Now, I can give you gamma also. So, I given you some, I will give you some number for delta, I will say delta should be 10%, right. So, I will say delta should be 0.1, right. I will give you the delta, I will say delta should be 0.1, I will give you the gamma also, okay. Now, solve for it. So, what does delta equal to 0.1 mean? That 90% of the time this event should be true, okay. So, I will give you a gamma, I will give you a delta, you find m for me.
So if you have the liberty to pick your hypothesis set, right?
Yeah.
So then this seems to say that you choose a very small k, right? Because it makes it easy for you to fix a high problem. Meaning the existence
To ensure
of,
uniform convergence, yes.
like, but that's not really
No, but then what this tells you is you choose a small hypothesis set
right.
to ensure uniform convergence, so that it will tell you what the true error is. Does not tell you anything about how good the true error is, okay. Right. So, that is why I kept reiterating to say what performance means in this case. Performance is not minimizing the error, performance is minimizing the error in predicting the error, okay. It's kind of circular, but we are trying to minimize the error in predicting the error, okay, that is all, or in measuring the error. Okay, it is all there, I mean that is easy. So, this is called the sample complexity, right. This tells you how many samples you have to draw, so that what? So, your all your classifiers are within gamma of the true classifier, right. The probability of that happening is at least 1 minus delta, right. So, these kinds of formulations are called PAC formulations, PAC. So, you know what PAC is? You know what PAC is? Probably, approximately correct, right. So, no, the probably part comes from that, right, and the approximately part comes from that. So, I am not telling you it is correct, okay, it is approximately correct, it is within gamma of the right answer, right, but is it always within gamma of the right answer? No, it is with a high probability it is within gamma of the right answer, right. So, it is probably approximately correct, right, but in many cases this is the best I can tell you, because there is so much variation in the samples that you are drawing, right, and the problem itself has inherently has noise in it, right. There is only so much I can do in terms of predicting it correctly. So, isn't this stuff interesting? So, another thing which I want to look at is I give you m and delta, okay. Can you solve for gamma? Right, I will fix m and delta, solve for gamma, what do you get? Fairly straightforward, right. Okay. So, likewise if you want to solve for delta you can try these things, right, but this is fairly easy stuff, right. So, what is gamma really? It is the error in the prediction of the error, right. So, it is epsilon minus epsilon hat is gamma. So, essentially I am saying that epsilon minus epsilon hat will be gamma will be yeah. Yeah.
Delta probability or that quantity?
So, delta is this quantity, 1 minus delta is the probability of not making a mistake. So, delta is the probability of making
So how do you get n greater than or equal to?
this one.
How did you get the next step n greater than or equal to 1?
So, what happened, I just solved this expression here and so what do I get? Delta, where I need to take E.
We have delta equal to 2k.
Yeah. So, see M should be equal to this to give you the exact delta probability, right, give you exact 1 minus delta probability, but I want it to be at least 1 minus delta, right. So, that is why I say it is greater than or equal to, right. So, I will get at least 1 minus delta if M is greater than, if M is equal to I will get delta exactly 1 minus delta, but M is greater than or equal to I will get something greater than 1 minus delta, right. So, that is essentially what we are looking at here, and so using the same argument what should we be looking at, right. So, my gamma so it should be greater than or equal to here, right, gamma should be greater than or equal to. So, my gamma should be at least gamma can be at most this small, right, gamma can be at most this small, but it can be greater. So, then I can give you that guarantee. So, that is essentially what we are looking at here, right. So, this is not needed. So, we will define H star to be H star is the truly the best classifier that you have, right, in the hypothesis class H, right. We will define H hat to be that classifier you will pick by doing empirical risk minimization, right. Epsilon hat is a classifier you will pick by doing empirical risk minimization, right. So, knowing whatever we know, can we write things right. So, epsilon hat, epsilon of H hat is less than or equal to epsilon hat of H hat plus gamma. Why is this true? Because of whatever we have shown all the while, right. So, I am saying that, right, I have taken enough samples M, so I can say with some probability this event will hold, right, because of my uniform convergence with some probability, that some probability 1 minus delta this event will hold, right, because this will be gamma close to the true error, right, the epsilon hat will be gamma close to epsilon, right. So why can I say this? So H hat is produced by doing arg min over epsilon hat, right. So that means that H star should either have a higher error than H hat or at least equal error. It can't be a better error than H hat, because if it had better error than H hat, then H hat wouldn't have been chosen. Right? Does it make sense? Right. This I am using by virtue of the fact that I did minimization here, right, and therefore epsilon hat H star should be worse than epsilon hat H bar H hat. Using uniform convergence again, right, I can peel out one more gamma from there, right. Does it make sense? What I have done here is exactly I went from here to here, right, I mean, from here to here. How did I write this gamma? Because of uniform convergence, right. Similarly what I did was I took epsilon hat H star and I said that it will be within gamma of epsilon H star, right. So then I added the gamma here, so I get 2 gamma, right. So all of this will hold with some probability, but I am assuming that I have taken enough samples that I have converged to whatever degree of accuracy I need, right. I have converged to some probability 1 minus delta, I have converged here. So once I have converged, so this will hold. So essentially what I have is that so what does this mean? So the true error of the classifier I produced by doing empirical risk minimization is within 2 gamma of the true error of the optimal classifier, right. Does it make sense? The true error of the classifier I produced by doing empirical risk minimization, which is H hat, is within 2 gamma of the true error of the classifier that is produced by minimizing the true error. This is essentially the optimal classifier, right. So essentially this gives you the guarantee that if I do empirical risk minimization, right, taking that many samples, right, then I will be within 2 gamma of the true classifier. Anything else I need to add? With probability 1 minus delta, right. So if I take at least this many samples m, right, so the classifier that I find by doing empirical risk minimization will be within 2 gamma. So where gamma is the number you plug in here, right, within 2 gamma of the optimal classifier with probability 1 minus delta. So that is essentially the result that we can have, right. So let us put this together and write a small theorem, and I can erase this, right, I will not be using this again. So right. So, essentially I have written out gamma from wherever we solve for gamma, yeah, here, right. I wrote the gamma expression down there, right, and we get this, okay, fine. But what is epsilon h star? Right, so epsilon h star is actually minimum over h of epsilon of h. So, this is essentially the best possible classifier that you can build, okay. So, now we have this result, we can go back and think about the question you asked some time back, right. If my hypothesis class is small, right, essentially what I will be doing is I will be searching over a small number of things to find the lowest error. So, it is likely that my solution, the best solution I can find in this class itself will be bad if my class is small, right. But if my class is small, the second term is small. If the number of things, if a k is small, the second term is small, but if my k is large, right, then the likelihood of me finding a small error solution is high, but the number of samples I need will also become larger, right. So, this is one form of bias variance trade off. So, if the hypothesis class is small, that means that regardless of how much data you give me, I will always be making some error because I have only a few hypotheses that I can search through. So, that is like a bias, you know, it is like doing linear regression kind of thing, right. And this is variance because the hypothesis class is very large, then I will need a lot of samples for me to estimate the error properly, right. So, that is the variance part. So, this is like one version of the bias variance trade off that comes in. So, that is the reason you need large hypothesis class, so that you can be sure that you have the right solution in there. But if you know exactly what is the solution you are looking for, then you are better off using a much smaller hypothesis class, okay. So, that is essentially the takeaway message here. Right. So, we already know what is the sample complexity you need for this result to hold for a specific gamma, right. So, here I mean the gamma is given by this expression, but if I give you a specific gamma, then say something like, okay, with some probability 0.1 I want to be at least 0.1 close to the true answer, right. With probability 0.1 I want to be at least 0.1 close to the true answer. So, what is the 0.1 close here? It is 2 gamma, right. So, it is 0.05, right, gamma should be 0.05, right. So, I will plug in 0.05 and 0.1 here, right, and I know what k is because of the hypothesis class I have chosen. I can always find out what the sample complexity m is. So, given a delta and a gamma, I can find m, okay. So, this kind of an analysis, this kind of sample complexity is sometimes called it is usually called epsilon delta, where because people usually use epsilon as a symbol for gamma, but in this case it will be gamma delta sample complexity or gamma delta pack analysis, because I fix the gamma, I fix the delta, I ask you for the sample complexity, right. So, this is sometimes called gamma delta pack, okay. So, this is assuming you have a finite hypothesis class. What do you do in the case of a infinite h? Any thoughts about how we would extend this analysis to an infinite h? So, in a practical setting, right, I will be typically implementing all my machine learning algorithms in a digital computer, right. So, this is a kind of a cheating argument, but it is fine, right. So, I will be implementing these in a digital computer, and digital computers, even though they are implementing an infinite class of things, they are limited by their numerical precision, right. So, let us say I use 64 bits to represent floating point numbers, and there are only a finitely number of finitely many classifiers I can represent with 64 bits, right. So, the problem is it is a large finite number, right, but I can still go back, and if you look at that number I have there, right, if you look at the m that I need, right, you can think of m as being actually, I can ignore a whole bunch of things here, but m is order of right. So, you can always say that, okay, regardless of how large my hypothesis class becomes, right, this is going to be log of that, order of log of that, so that will be a significant reduction, right. But unfortunately my hypothesis class becomes exponential. Suppose I have d numbers I need to specify one classifier, right, and I have 64 bits, right. So, how many hypotheses do I have? So, how many bits do I need for representing one classifier? 64 times d. So, how many do I have, and then how many classifiers could I have? 2 power 64 times d, that is k, right. I plug in k here, then it becomes d, it becomes order of d. So, if I have 1000 parameters, then I need about order of 1000 samples, not bad.
It will be 1000 multiplied by a very large
That's 1 by gamma log delta and all that. I mean, it depends on what you expect out of it, right. You choose a large gamma, large delta. I am just joking, right. So, yeah, of course you always have those things, right, the gamma, delta and other things actually play a role there, right. But so think about it, right. I mean, I have d parameters, I mean, don't I need to get at least order of d samples to solve the problem? Okay, how do you think I can do it with less than order of d? If I am able to do it with less than order of d, then many of my parameters are all tied together and they are redundant, right. So, this is the power of the big O notation. You can hide a lot of things under the big O umbrella, because you are hiding all your 1 by gamma squared and log of 1 by delta, you are hiding under the big O umbrella, but it is not a bad thing, okay. So, this is one way of thinking about it, right. It is not the greatest way of thinking about it, but there is one way of thinking about it. In fact, people use the rule of thumb, right. Suppose you are training a neural network which has say 10,000 weights, they use the typical rule of thumb they use is you need at least 10x the number of weights. So, if you have 10,000 weights, you need 100,000 data points at least, right. And in fact that is a very useful rule of thumb if you are only using feed forward neural networks, right. So, remember this, if you count the number of weights you have and 10 times that, how many data points you need at least for you to give anything useful. But then there is a better way of doing it, right, called the Vapnik, Chervonenkis dimension, the Vapnik Chervonenkis dimension, otherwise known as the VC dimension, right. So, given a hypothesis class, we can define the VC dimension of the hypothesis class. I will finish in a few more minutes. Okay. So, before I define a VC dimension, I need to introduce the notion of shattering, right. So, given some set of points, okay, gives let us say some set S, I give you some points x1 to xk, let us say, a hypothesis class H is said to shatter the set S if for every labeling you can give for that set S, there is some element in the hypothesis class which actually separates the classes, binary classes. Okay. So, every possible binary labeling that you can give on this set, okay, I have a hypothesis in my hypothesis class that separates it from one class from the other. Okay. Is that clear? So, let me draw a picture that will make it clear. Let us say that, so that is my set S, okay, and in my hypothesis class is all straight lines. Okay. So, think of all possible labelings I can do for this, right. Right, I can basically say, okay. So, everything to one side of the line is plus, everything to the other side of the line is minus. Great. So, now what do I do? Everything to one side is plus, everything to the other side is minus. Okay, so, likewise I can keep going, I will keep going as long as there are different number of colors here, and then you guys can kind of intuit. Right. So, given the set of 3 points, you can just see that, right. So, if I flip the plus and minus, that is exactly the same, right. So, you will have to only worry about the unique things, right. So, if I flip the plus and minus, it is just the same. So, if I make this plus and these two minus, the same thing will work, right. So, is there anything else that we need to consider? So, plus plus minus, plus plus plus, plus plus minus, that should be a minus, right. Right. So, what that will work, right. Anything else? So, I have to consider 2 pluses and 1 minus, 2 minus and 1 plus is just flip of it, right. 3 pluses I have considered and 3 minus is just the flip of 3 plus. Okay. So, anything else that we have to consider? That is it, right. I left out it, but anyway, even if I left out something, you can make it up, right. So, you can easily see that. So, straight lines, the hypothesis class of straight lines shatters 3 points in space, right. What about 4 points?
A single straight line is
So, yeah, we are talking about single straight lines. So, what about 4 points? Is there any configuration of 4 points which can be shattered by single straight lines? No. There are no configuration of 4 points that can be shattered by single straight lines. That then automatically applies there 5, 6, 7, 8, nothing, right. So, the VC dimension of a hypothesis class H, okay, is the size of the largest set that the hypothesis class shatters. Note that the size of the largest set H shatters, that does not mean that H has to shatter all points of that size, right. Even in the 3 case, collinear points I can't shatter, right. So, if my 3 points are like this, right, and I label this plus, minus, plus, there is no straight line that can separate this, right. But there is some configuration of 3 points, in fact lot of configuration of 3 points which I can shatter, and therefore the VC dimension of straight lines is 3, right. What about VC dimension of pairs of straight lines, parallel lines, not arbitrary pairs. Let us say I give you parallel lines. What is the VC dimension of parallel lines? 2 parallel lines. They have to be parallel, and however you want you can rotate it, but they have to be 2 parallel lines. It can do 4 for sure. Can it do 4? It can do 4 for sure. I mean, you can always keep one of them as redundant. With one straight line you can try to do as much as you can, and when you get to XOR you use two straight lines, right. So, everything else is doable by one line, right. Only the XOR case where this plus plus and minus minus you can't shatter with a single line, right. Remember perceptron, right. So, it is exactly that, right. I mean, so you can't, for that you need parallel lines. For everything else you have one line there and keep on the next parallel line at infinity, you are fine, right. What about 5 points? Now you can see why we can ask all kinds of interesting questions in this, right. So, I can give you this kinds of thing. I can give you, next I will say, okay, instead of looking at parallel lines, look at quadrilaterals, right. So, if it is inside the quadrilateral it is class 1, class positive, if it is outside the quadrilateral it is minus, okay. Now, what is the VC dimension of that, right. In fact, there are uniform convergence results for VC dimension as well, right. So, I will have the TAs put up this write up online. Of course, there is a whole bunch of other things, other material you can find out online, right. I am not going to do the result or anything, it is pretty complex derivation, right. But then the nice thing about it is that at the end of the day, just like we have sample complexity is polynomial in the number of parameters, right. You can show even with VC dimension that it is polynomial in the VC dimension, right. So, if the data has a finite, I mean if the hypothesis class has a finite VC dimension, right, the uniform convergence results require you to have order of the VC dimension number of samples, right. And typically it turns out that for most kinds of classifiers, most kinds of reasonable classifiers that are out there, the VC dimension will be of the order of the number of parameters in the classifier, right. So, if you think about it, straight lines, how many parameters are there in this case? 2 or 3? 2, slope and intercept and slope, that is all you have, right. So, we have 2 parameters, right, and the order, the VC dimension is 3, close, right. It will be close to the number of parameters that you have, right. So, and it turns out that is why I said 10 times the number of weights in a neural network, right, and all of these things, and so you can get those kinds of rough intuitions, right. So, I will stop here. So, if you have any questions, feel free to fire away.
So, how does this work for regression kind of problems? As in, how close are we to the best possible?
So, we could do pack-like bounds for regression,
Okay.
right, but VC dimension is defined typically for classification problems. Yeah, I mean you can coarsen the regression problem a little bit and then try to do VC dimension like results. As far as I know, VC dimension is more for classification like problems, and pack results you can do for regression, because you essentially are trying to look at, so we defined a very specific Bernoulli variable, random variable here and did it, but it need not be Bernoulli. So you could define any random variable, you could with whatever distribution. That's the amazing thing about the Chernoff Hoeffding bounds, right. So and the result holds on the expectation, the parameter mu, whatever is the expectation of the distribution you are looking at. So the empirically evaluated expectation will be close to the true expectation. That's the result that you have. So with that you can change your random variable definition and you can get something appropriate for regression as well.
In hypothesis the H1, H2, Hk we have
Ah.
are they different classifiers or the same classifier with
Different. What does it mean? When you change the parameters, it's a different classifier as far as I am concerned.
No, he means same family of classifiers.
It depends on how you define your hypothesis class, right. So at the end of the day, what I am really interested in is what is the decision rule that the hypothesis class is entailing for me, right. So I can say that, okay, I am going to define a hypothesis class which is a mix of decision trees and SVMs or something. It's up to you, but typically you define a hypothesis class as a single family which is just differentiated by the parameterization. Okay, but we don't actually take a call on that. All I am telling you is that, okay, given k hypothesis, right, how are you going to find out so what I am finally at the end of the day, what I am interested in, like I said, the decision rule. Okay, given a data point, what does it assign it to? Whether you derive the decision rule by means of using a logistic regression, or whether you derive the decision rule by means of using I don't know, LDA, I mean, doesn't matter for these kinds of complex analysis. Right? How you got to it doesn't matter for me. Only in this context, right? I mean, otherwise it matters. But in the context of this complex analysis we are doing, it doesn't matter. Which is why our finite precision arithmetic is a little disappointing, because there I chose d parameters, right. I mean, if I had gotten it from some other, I could reparameterize things and I can increase the number of parameters for representing the same decision surface, right. I mean, I want to define a straight line, but I can actually increase the number of parameters I am going to use for defining the straight line by saying that wherever I have ax squared, I will have minus ax squared, right. So now I will have two more additional parameters for me to define, one should be a, another should be minus a, and it will take out the dependence of x squared. So it will still be a straight line, right, but I will increase the number of parameters. And going back to our finite precision arithmetic argument, I would also have blown up my complexity, which is actually not correct, because all I am interested in is only the decision rule. That is why the finite precision thing is a little unsatisfying. But here we did not tell you how you represented the line, right. So the VC dimension definition does not require you to know how you represent the line, right. At the end of it, you know that, okay, so this is the set of hypothesis I want to represent, but the most compact way of representing the hypothesis, that many parameters I would need. So that is essentially what we end up with, right. So we do not have to worry about how you get to it. Anything else?
For this VC dimension thing, so if your hypothesis set is rich, as in rich in the sense that you can have multiple classifiers.
Yeah.
So then the VC dimension will be the one for the most powerful classifier. I mean, the one which.
Yeah. I mean, I can choose any classifier I want from my set, right, for shattering the data points.
Correct, yeah.
So yeah, in effect, it will be the one corresponding to the quote unquote most powerful.
Right.
I mean, what do you mean by most powerful, Matt? Yeah, the one that can shatter the largest.
Correct, yes.
There you go. So that will be the VC dimension.
Right.
So the VC dimension, if it can shatter sets of any arbitrary size, VC dimension will be infinity. So if the VC dimension of the classifier is infinity, none of the analysis will work, right. All the VC dimension analysis works assuming that the VC dimension of the classifier is finite. Good. Fine. So I should point out that most of the classifiers we looked at do empirical risk minimization, except, anyone know? SVMs. except SVMs. SVMs do what is called structural risk minimization, because they have an additional constraint that is there, that apart from the empirical risk they also try to minimize the solution size, right. They try to minimize the norm of the weight vector, right. So, that actually gives rise to a different kinds of minimization. So, this does not do empirical risk minimization, they do what is called structural risk minimization. So, you know who came up with SVMs?
Vapnik and Chernoff.
No, not Chernoff, only Vapnik. So, yeah, so Vapnik came up with SVMs, right. So, and others, he came up with SVMs from this VC dimension stuff, right. So, he said, okay, with structural risk minimization, this is the best you can do. Okay, so we need to have a different way of doing the minimization of the error, and then he motivated it, and then he came up with empirical. I mean, other way around. So, with empirical risk minimization, this is the best you can do. So, let me go and do something else, and then he came up with structural risk minimization, and then he derived SVMs from that. Okay, if you read the Vapnik's original presentation of SVMs, right, it will not look anything like how we present SVMs nowadays. Right. So, if you remember, we started off with perceptrons and separating hyperplanes, and then we went from there, right. No, he starts from the theoretical side of things. Okay, he says, okay, if you do empirical risk minimization, this is the best you can do. Let me see what else can I do so that I can improve on this, and then he came up with structural risk minimization. Okay, and then he derived all those stuff. Yeah. Okay.